Okay, let's get started. So our next talk is by Amin Farjudan, and it's tell us about continuous domains for function spaces using spectral compactification.
Thank you. So yeah, my talk will be primarily on domain theory. There will be a little bit of stone duality and a little bit of topology in it as well. Now, I'm just assuming that most of you are familiar with the close connection between topology and the theory of computation. Maybe the computer scientists among you find it quite natural, but when I first realized that, it was quite a pleasant surprise. But anyway, it can be seen clearly in domain theory, how topology and theory of computation come together. I'm going to focus in a way in the sense of where the motivation came from and its application of what we're going to talk about. On domain theory, as it's been applied to concepts and operators of mathematical analysis. So domains provide a natural computational framework for mathematical analysis, but I mean, it's really non-algebraic domains that have proven to be more natural. As far as I know, the work was initiated by Abbas Edalat in 90s at Imperial College, and the earliest paper that I know, say major paper, is on dynamical systems. But interval domain or interval lattice actually appeared in Dana Scott's paper, Outline of a Mathematical Theory, and Moore's book on interval arithmetic is also one of the, I think, 4 or 5 references in that paper. So this has been around with us. It's just that, Edalat kind of took it to the next level. There has been plenty of work since then, but I'm going to only mention these 4 here because they're related to the talk today. Differential equation solving, stochastic processes, reachability analysis of hybrid systems, and robustness analysis. Now, when you work with these problems in mathematical analysis, at some point you have to deal with a topological space. And the nature of that topology determines your fate, essentially, whether you get a good computational model or not. Now, one of the key properties is local compactness. If you have it, usually things go better. But in many important applications, we don't have local compactness. For instance, whenever you're dealing with infinite dimensional Banach spaces, PDE solving, functional analysis, working with space of probabilities, L1, whatever. So the question is, if we don't have local compactness, then what should we do? In a way, well, nothing, because you don't get a domain. But we can, this is a very loose term. We can think about a substitute construction. Well, on the one hand, you've got a partial order, which is not a continuous domain. On the other hand, you construct the domain and make sure that these two are related, say, by an adjunction. But we will see that in more detail later on. This idea has already appeared in, for example, robustness analysis of systems with state spaces that are not locally compact. Another application is in solving initial value problems with temporal discretization, like Euler's method, Runge-Kutta. I'm going to spend a little bit of time talking about this just to give you the idea where this all came from. So imagine you've got this initial value problem, very simple one, T0 in R, Y0 in R, F a function from real to real, just continuous. That's enough. Peano's theorem tells us there is a solution. If it is Lipschitz continuous, then there is a unique solution, etc., etc. Now, assume that again, by some way, we know that there exists a solution over this lifetime of T0 to some capital T. In a domain theoretic setting, when we want to solve this IVP, we look for a solution in the space of functions from the lifetime T0T to the interval domain IR, which is just the partial order made up of these compact intervals. We put the entire space right at the bottom, because we always need that. And the order relation is the superset relation. And the reason for that is that a narrower interval is more accurate than a wider interval. So we take superset relation. If you take that IVP and integrate both sides of it, you get this integral equation, which tells you how to go in steps. And out of that, you can think about a general schema for solving for validated solution of initial value problems. So imagine you take a partition of the lifetime t0 to t, and then at point t0, we know the solution. After that, if you want to go from any one of these qj's to qj plus 1, you've got to go by this relationship where this I is an interval enclosure of the integral factor right up there. Okay, so it's just you take conservative enclosure of solutions and just go forward. And then you would say, okay, this is by itself a little bit not functional enough, it's imperative. How can I get a fixed point formulation of this differential equation solver? So you would say, okay, just, imagine you've got this operator which takes y and assigns these values to it. If this phi, I don't know how to pronounce it, if this phi has got a fixed point y, then that y must be the solution of the initial value problem. Okay, now here's the important bit, and it tells us why we get into all the trouble with non-core compact spaces and all. So imagine we've got this IVP, and we know that this is the real solution. I mean, we don't know it. This is the real solution, but we don't know it. But assume that this is the real solution, and by some way, right at the beginning, we know that this solution must lie between these two green bounds. Somehow we know. And then we pass that on to this operator. What does it do? At point t0, which happens to be 0. So for simplicity, I've taken t0 and y0 to both be 0. So at first, well, it's difficult for you to see, but it put a little bullet here. But then when it wants to go forward, it has to look at what that initial approximation, the green one, gives us on Q0. So it starts from the bound and moves forward. And then to go from Q1 to Q2, again, it has to look at what that green bound tells us. After that, it goes kind of autonomously, but at every discretization point, it has to go back to the outer approximation. And if you look at it, now we've got these two bounds, the black one and the blue one. The black one, which is the upper bound, is not upper semi-continuous. The blue bound at the bottom is not lower semi-continuous. If the topology on the lifetime is taken to be Euclidean, then these two bounds must be upper and lower semi-continuous respectively. So there's a problem. And if you continue for another round with this flawed approach, anyway, this is flawed, but you can see that now the enclosures are getting tighter and tighter, but still the problem remains with the semi-continuity. Okay, so we'll look at it from a bit of a distance. We have this function space. On the right-hand side, the interval domain, we know that it must be equipped with the Scott topology. No worries about that. What about the lifetime? That is the important one. Because of the semi-continuity problem, we cannot consider it with the Euclidean topology. And if you think about it, the coarsest topology with respect to which these enclosures that I showed you on the previous slide can be continuous is what is called upper limit topology. Actually, I'm not sure if it's the coarsest topology in a way, but yeah, I mean, if you allow the discretization points to be arbitrary, then this becomes the coarsest one. Anyway, the point is that we end up with the upper limit topology, and the basic open sets of this upper limit topology are very minor modification of the Euclidean open. So it's half open intervals. Open on the left-hand side, closed on the right-hand side. the gist of it, or the main point, is that this topology is not locally compact. So that causes a problem. But for those of you who may not know why not being locally compact causes a problem, so we have got this theorem. This theorem in its form doesn't appear in the paper that I've cited, but the proof can be found in two different parts of the paper. So I've just written it as a theorem. If you have a topological space X and a non-singleton BC domain D, then the function space is a BC domain if and only if X is core compact. Again, if you've forgotten what core compact means, it's just the lattice of open sets is continuous. But you don't even need to know that, because in our setting, really core compactness means local compactness. Because all the spaces that we work with are sober. So in sober spaces, core compactness is local compactness. So essentially, when we don't have local compactness, we have a problem. So yeah, in summary, so far, the upper limit topology, if you use that, you don't get a continuous domain of functions. So you cannot do proper computation. Now, as I said, okay, if you don't have a domain, you can find a domain which is related to this. If the function space doesn't give you a continuous domain, why not find a continuous domain which is related to this by, let's say, an adjunction? So here, the basic idea is this. If the problem is that X is not core compact, then why not find another space? We call it X hat. I hope you can see the hat, which is core compact. X can be embedded into it as a dense subspace. So it's like core compactification. And of course, we want these two function spaces to have some relationship with each other. So this is the function space which is not a continuous domain. This is the one which is a continuous domain, both by the previous theorem of Erker, Riscardo, and Kaimak. And they're related via a Galois connection. That Galois connection allows us to say that, this is a good substitute. If we do that, then we can do our basic computations in the DCPO, which is not a domain, but we can do computable analysis in X hat to D, which is a continuous domain. Of course, it has to have an effective structure on it, so it has to be an effectively given domain. But usually when you get to this point, you have covered like 90% of the distance anyway. Okay. What is this Galois connection that I mentioned here? It's actually a special case of a general Galois connection. For the general Galois connection, all we need is two topological spaces X and Y and a dense embedding of X into Y. Now, here I've written, T0 spaces just to make the presentation simpler, but you can even weaken these conditions. But anyway, let's say T0 topological spaces, you've got a dense embedding of X into Y. And you define these two maps. One of them takes maps from Y to D and gives us a map from X to D by just composing it with this embedding. The one that goes from X to D to Y to D is a little bit, it looks a little bit more unfamiliar, but for domain theorists, this is very close to what we know as envelope, I think. Yeah. So yeah, for example, because this is a dense embedding here, whenever you take an open set in Y and look at its inverse image, it must have an intersection with the, it must be non-empty. That's what I mean. So with these two, we get a Galois connection. As I said, the only thing that you need is to have a dense embedding of X into Y. And the Galois connection is good because the left adjoint is surjective, the right adjoint is injective. Composition of the left and the right is the identity. And the left adjoint is continuous. This comes from like general results in domain theory. But one thing that I want to point out is the right adjoint is continuous if and only if it's a space that we are not interested in. That's it. Yeah. So the right adjoint is continuous if and only if X is core compact. But then when X is core compact, we don't have to go through any of this. So now we can have this working definition of core compactification, which is exactly like compactification, but we just require that this X prime be a core compact space. So say it's a core compactification of X if and only if X can be embedded as dense subspace of X prime. That is enough for us to get everything that we want. But some classical compactification methods definitely give you core compactification. I mean, all of them actually. But when you look at them, for example, one-point compactification. The one-point compactification of Euclidean spaces is where you just add an extra point to your space. So for example, for real numbers, you just tie it up with a common point, and then you define the usual topology on it. It works only for non-compact, locally compact spaces. Hausdorff spaces, I should say. It gives you the right result only for these spaces. A more general example is the Stone-Check compactification, beta X, that's what I use, which works for any Tikhonov space. But the problem is that, it relies on axiom of choice, so you don't get any concrete description of the elements that have been added to the space, which is not useful for computational purposes. So instead, we take another route. We say, okay, you have a space which is not core compact, but there are open sets in it that you really want to work with. Now, try to come up with a set of open subsets of your space and make sure that it forms a base for the topology and is closed under finite unions and finite intersections. We call that a viable base. Again, this is done kind of ad hoc term, but it makes sense in this talk, hopefully. Because we say, closed under finite unions and intersections, it means that it must have the empty set and the entire space. So it's a ring of sets for those of you who know what that means, but in any case, it forms a bounded distributive lattice with the meet being intersection and join being the union. There's always at least one viable base. Just take the entire topology. You always get a viable base. Okay, now the key point is that we've got a bounded distributive lattice. Now we can do, we can construct a space and do topology. Because we have these equivalences of categories. I will talk a little bit more about what these things are, but if I have a viable base here, bounded distributive lattice, I take the ideal completion, I get an algebraic fully arithmetic lattice, and then I apply the PT functor, I get a spectral space, a topological space. That will be the space that we're looking for. So I go to the definition now, then I go back to explaining what these things are. So assuming that X is a topological space and omega 0 is a viable base of X, then by spectral compactification of X generated by omega 0, we mean the topological space that you get out of applying ideal completion followed by the PT functor. And as we can tell, what you get depends on omega 0. That's why we say generated by omega 0. Now, a quick explanation of what you see here. On the left-hand side, you get bounded distributive lattices, and the arrows are bounded lattice homomorphisms. In the middle, you get algebraic arithmetic lattices, which we call fully arithmetic when top element is also way below itself. And the arrows are frame homomorphisms. And on the right-hand side, which is the important one, is the so-called spectral spaces with the spectral maps. Spectral spaces are, by definition, compact, sober, coherent. So these three mean like the usual topological spaces that you work with. The fourth one, which is strongly locally compact, that is a little bit odd. That is not the kind of topological spaces that we work with every day. Spectral maps are the ones that preserve the spectral structure. So if you take any compact open set, the inverse image must be compact open. Compact open really means compact and open. Okay. So as I said, the one feature that stands out is this strongly locally compact. We say that the topological space is strongly locally compact if its topology has a base of compact open subsets. No, not just open, but they have to be compact and open. And it can be shown that, if you have topological space, any subset of it is compact open if and only if it's a finite element of the lattice of open sets. And by that, you can show that a topological space is strongly locally compact if and only if the lattice of open sets is algebraic. So again, I said non-algebraic domains primarily in mathematical analysis, but actually, as you can see, sometimes we have to go through algebraic lattices anyway. So it's not like they're completely separate. This PT functor, a quick reminder. So this is a functor that gives us a topological space out of a lattice, but you can think of the lattice of open sets of a topological space if you haven't seen this kind of thing before. So for any complete lattice, by a point of the lattice, we mean a completely prime filter. There's a nice picture of it in the Abramsky and Jung. I hope I can remember it. I don't know. It looks something like that. Sorry about messing it, but it was that. It's completely prime filter. You cannot get to this filter by forming a supremum of arbitrary sets. And the topology that we consider on it is, by some people, it's called whole kernel topology, where all the open sets are parameterized by elements of, so U ranges over the elements of the lattice, and for each U, you get this set of O sub U, the set of points. Now, these points are completely prime filters. Those points that include a specific U here. Okay. I'm not going to go through what the morphism does. It's not necessary here. So now if we look at the whole kernel topology on the spectral space that we have obtained, it will be of the form O sub I, but this I is now an ideal over omega 0. So we get the set of all those points that include a specific ideal. With that, we can show that for a base of the whole kernel topology on this spectral space, all we need to take is the sets of the form O down arrow W. These are principal ideals where W comes from omega 0. So if you choose your omega 0 carefully, make sure that it's countable, for example, then the spectral space that you get is going to be second countable, which is very useful for computation. Now, to give you an example, I can give you the example of this rational upper limit topology, which is essentially upper limit topology, but we take half open rational intervals. If you take all of the topology, you end up with a space which is not second countable. So instead, we take something more reasonable. For example, finite unions of these half open rational intervals. With that, we get a second countable spectral space. And because this omega 0 can be effectively enumerated, blah, 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 then we get a very good computability structure there. Okay, so we used that rational upper limit topology before for IVP solving, but the approach that we had before was based on abstract basis. Now, in the work that I'm presenting now, we've gone through another route. We've gone through the route of compactification. So we can show that if X is a T0 topological space and omega 0 is a viable base, then the spectral space that we get is truly a core compactification in the sense that X will be densely embedded into X hat. And as we will see in theorem 15 of these slides, abstract basis approach and the compactification approach both give us the same outcome. But for the function space, to see what it's like, we've got to say what a reasonable basis for that function space looks like. And for that, we need a reminder of what step functions are. So imagine X is a topological space and D is a pointed DCPO. Pointed means it has a bottom element. For any element B in the DCPO and an open set in the topological space, we define this step function, you can read it as B multiplied by the characteristic function of O, which for every X in O gives us B. For every X outside of that open set, it just gives us bottom. So an example of it is when you take the B to be this interval 0, 1 in the interval domain, the open set will be this open set minus 1, 1. The entire space is from -2 to 2 and then to the interval domain. So as you can see, in this open set -1, 1, you just get this compact interval 0, 1. Outside of it, on the two sides, you get bottom. Put finitely many of these together and you will get a step function. So a step function is finitely many single step functions, or the join of them. The point is that if you start with topological space and a viable base omega 0, and you have a BC domain and a basis D0, these two can give you a description of a basis for the function space, where you take the join of finitely many single step functions, make sure that these are consistent. The important point is that they're parameterized by elements coming from omega 0 and D0. So again, if you make sure that your viable base is countable and your domain, BC domain D, is omega continuous, then the function space will also be an omega continuous domain. The way below relation over step functions can be described in a kind of intuitive way. So for single step functions, B x down arrow omega B prime x O down arrow omega prime. So we have this relation if and only if W is subset of W prime and B is way below B prime. The important point is that we've reduced this way below relation to just the subset test. But for the more general step functions, it becomes a little bit more involved, but still it's essentially checking whether one open set is a subset of another one. That gives us an abstract basis of, joins of finitely many single step functions. And with this relation that I just described to you, you can get an abstract basis. And if you form the rounded ideal completion of that abstract basis, you get a domain which is isomorphic to the domain that we had from compactification. So two different routes, abstract basis, compactification, they give us exactly the same result. Now, if you go back to the Galois connection, again, this makes sense now. This is the compactification. But yeah, I'm going to move on to a few concluding remarks. So what we have done is we have presented a computational framework for function spaces where the topological space is not core compact. For example, upper limit topology or any infinite dimensional Banach space. When we do computable analysis, we look at the continuous domain x hat to D. But for example, if you work in type 2 theory of effectivity, you would work with admissible representations of the function space D to the power of x. I'm curious to know how these two topological spaces, this one and that one, they relate to each other. For example, could the admissible representation be a restriction of the stud topology here? In terms of applications, well, ODEs were the things that we started off with. We believe or expect PDEs to also, the construction to be useful in PDEs as well. Stochastic processes with right continuous maps, there you have to look at lower limit topology, which is again not core compact. And yeah, one last remark. So our construction is a special case of Smith's stable compactification. In his paper, if you read it, he considered these things called quasi-proximities, and there's a special type of them called fine quasi-proximities, which give us spectral compactification, even though in the paper that we have written, we don't mention quasi-proximities at all. But I'm curious to know, so IVPs led us to work on spectral compactification. I'm just curious to know if there's a similar application, concrete application, which necessitates, if that's the word, using stable compactifications which are not spectral, or in other words, using non-fine quasi-proximities. If you know such an application, please let me know. Thank you.
quite a lot of great questions.
You know, you're trying to make some kind of bridge between things. Have you looked at what the guys are saying about dynamical systems? I mean, I liked very much to see the 4 papers that you showed about dynamical systems using domain theory and related ideas. But have you looked at what the guys in the ACT are doing with dynamical systems to see if we can do some sort of clever connection with that? Because, you know, there's an awful lot of dynamical systems being discussed there too.
Yeah, no, I don't know that, but I'll be interested to know that. Yeah, thanks.
But I thought maybe you had, I mean, that's the point of having the 2 conferences side by side, that we can see things from one side to the other.
Yeah, sure.
Okay, thank you. We want to make it. Thank you again. Thank you.